Current slide. All right. Before we get going on this today, let me say this. This class is one of my better classes. We got getting research papers in, but still not half of you have turned in a research paper, so please get those in. The first quiz, I'm still missing 2, 3, 4, 5, 6, 7, and so please get those in. Of course, I'm probably preaching to the choir here because I bet you most of you have got those in. Your first test, I think I have all the grades posted. So if you don't see a grade there, it's because I wasn't sure if you're coming back or not. So if you don't see a grade on Blackboard for you, but you are finished, let me know, and then I'll put your grade out there. But I didn't want to put a grade if you were coming back and going to improve that grade. So, all right. I don't know if they're going to open midterm progress reports or not. I haven't seen if they have. If they have, I haven't seen it. But if they do, I have to report anyone who has a D or F at midterm. Hopefully none of you will be in that category. The most likely ones are those who haven't turned in anything. You'll definitely be in that category. Okay. It doesn't really cost you anything, except maybe a little bit of hassle about, do you need tutoring? Do you need counseling? Do you need help with this, that, or the other thing? Which may not be a bad idea, but if you don't want that, go on and get something turned in. Okay. There is a faculty meeting this Thursday at 2 or something around in there, but they say we're not supposed to cancel classes. But you might want to check and make sure if you have a 2 o'clock class on Thursday that it is still meeting. It should still meet. They put that in the email that if you have class, go on and meet the class, and they will deal with the other later. You can catch up what you missed. And then the other thing is Friday morning. Normally I have office hours on the Birmingham West campus, 8 to 12, but this Friday I have an eye appointment right across the road here at the UAB West Hospital. Which I thought it was going to be at Eye Foundation Hospital, but they said no, he's out here this Friday, and so I will be at that at 8:15. So I'm guessing that'll take at least an hour, so let's say 9:15. Then I'll be traveling back to Birmingham West. Hopefully we'll get there by 10 o'clock, plus or minus some. So I'll be there at least 10 to, or well, somewhere around 10 till probably well afternoon. So, any questions before we get going today? All right. Now, last time we were talking about transformations, okay? 2.2, the title of it is Polynomial Functions of Higher Degree, and we're looking at graphs of polynomial functions and started off talking about transformations. So, it says sketch the graph of each function. And my question to you is, how would we begin this one? F of x equal, get my pen set up, minus x to the fifth. You have two options. You can just do it brute force, maybe 3 options, or you can sketch the parent function and then adjust that, or you can think through the parent function and try to go from that. So you tell me how you would begin to graph the A1 here. Minus x squared, minus x to the fifth. Okay. Tell me how you would begin. Anybody? You're not going to begin.
It's odd.
Second?
It's odd.
It is an odd function. You're absolutely correct. Which means?
Y-axis.
What's that?
Reflects over y-axis.
No, that's even. That reflects on the y-axis. It reflects about the origin. Okay? Odd function reflects about the origin. Now, what that means, we can do evaluations on one side and just duplicate on the other side in the opposite direction. That's where an odd function comes into play to help us out. Okay, but we still need something to graph. How would you begin graphing?
Table.
Second?
Table.
Table. Okay, we'll set up a table, sometimes called the T-table. X here, and we'll put f of x here, which is your y, right? So give me an x. 0. All right, I like 0, okay? And what would be your y value, your f of x? When you plug in 0 for 0. Excellent. So I can plot that on 0, 0 right there. Got it? Next. 1, okay? And what do you get when you plug in a 1? A negative 1, okay? Now how do I plot that one? How? Second? Okay. Don't think so. It's this one. You go right 1, down 1. Okay? Now, I didn't do my scale too well, but I'm going to put it right there. Okay? Now, because it's an odd function, you can go left 1, up 1. Just exactly the opposite because it's an odd function. And you can plug that in if you want to. Put in a negative 1. Negative 1 to the 5th is negative 1, but you negate that and it becomes a positive 1. So negative 1, 1 is also 1. You didn't even have to think about, but we did. Next. 2. All right. Bad news here, Bears. Huh? No. What happens if you plug in a 2? 2 to the 5th. 32. Woo! Can't plot it. But then you have the minus in front, so it becomes a minus 32. So it's somewhere way, way, way up there. So here's what this function is doing. It's coming down here like this, flattening out pretty much around 0, and then going downhill really quickly. That's what that looks like. Now, that should be up here on the axis. My pen doesn't cooperate very well, but that's basically what it looks like. Make sense? Yes.
So how do you know it's flat or not?
Because it's such a high power here. The higher the power, the more sharply it goes up and down past plus or minus 1, and the flatter it gets in between plus or minus 1. That's what we saw. Let's flip back a couple of graphs right here. Here is x squared, just comes down and kisses the axis there. X to the 4th comes down and kisses it, but it lingers. No, I'm sorry. Okay, but it goes up. It's much longer in the hanging around the x-axis and then goes up much sharper outside. Same thing here. Here's x to the 5th. X cubed comes up and just crosses and comes on up. X to the 5th comes up more sharply here and then lingers longer here and then goes up more sharply there. That's just how it looks. And mine isn't exactly to scale or anything, but it just gives you the general idea. Now, I want to pick a different, this was minus 32. We didn't write it down. There's what your 2 gave us. What would negative 2 have given us? Positive 32. Yeah, exactly. Everything's the opposite. All right. I want to do on the same scale the second one, h of x, or you want me to start over? You tell me. Huh? Start over. Okay. Everybody got this one? For me to erase? Okay. Give you a minute. Or 2. Or 3. Take as long as you need. While I'm waiting, it seemed like to me, I may be wrong, that I saw, yes, at least one person who had done the test, and I did not have a quiz for you. Did you bring it? Okay, all right, please do that. Let's see, was there anyone else? I thought there was more than one, but I don't see them now, so maybe I found everything. Okay. Got everybody caught it now? Okay. So let's clear this screen and go on to the next. And this time, looking ahead into my crystal, my vague little ball here, I will see, I'm going to put the axis way down there. Anyone have an idea why? Yes, this thing's always positive. Okay. Now, how would you approach this one? Go back to your good old table, or you have another guess? Say again? It's going to look like a parabola. Not quite, because it's going to be steeper outside plus or minus 1 and flatter between plus and minus 1. Except it's not going to be plus and minus 1, is it? What else do you notice about this? What's that? Yeah, it's always going to be positive. Got that. But what else?
It'll be shifted left.
Shifted to the left how much? 1. All right. Shifted 1 to the left because of that. Plus 1 there dealing with the x that shifts to the left. So there's going to be the center of it. And then from there we go up. Now this has symmetry, but it's around that line, x equal negative 1. So you will go here and here. Okay? And we could have done that real easy for this one. Plug in x equals 0, and what do you get? 1. 1 to the 4th is still 1. So yeah, that confirms it. And we know we're symmetric about this axis of symmetry, which goes through x equal minus 1. So therefore, the one on the other side works too. So you can continue, or it's pretty easy here. Just plug in 1. That's the next unit out here. 1 plus 1 is? Oh, good. Okay, high level math today. Okay. All right. And 2 to the 4th is? 16. Okay, I think that's going to be off scale already. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, way off scale. So at 1, it's going to be 16, so somewhere way up there, coming down real sharply, and then flattening out here near the x-axis, and then going up real sharp again. That's a pretty ugly drawing, but you see what's happening. Horizontal shift, 1 to the left, and then you have your parabola-looking shape. Does that make sense? We could have done a table and gotten the same things, but just analysis of this will give it to us as well. Any question? And by the way, you can see LarsonPrecalculus.com, absolutely free website. You don't need a code or anything else for an interactive version of that kind of graph. So if you want to see and hear the author or somebody that works for the author work through it, you can do that. All right, there is a checkpoint at the bottom of the page. It has 4 examples, so I would highly recommend practicing on those. Let's see how they proceed, because they do it. Can I go on and erase this now? And you want to see how the ugly graph looks. Okay. Here's the first one. Ha! There we have it. There was our minus x to the 5th, because your negation sign here, what would have been looking like this, just flips across the x-axis and looks like this. Okay? When x is very negative, your f of x is very positive. And when x is very positive, your f of x is very negative, because that minus sign flips it across. X to the 5th means you go up more sharply plus or minus 1, and you are a little bit flatter around x equals 0, or the beginning point. Does that make sense? Everybody got it? Okay. Here's the second one. And as you said, shift left by 1. So you start at minus 1, 0. That now becomes your axis of symmetry. Okay, because that is like a parabola, in that it does have an axis of symmetry. And anything you've got to the left, you have a corresponding point to the right. And again, outside plus or minus 1 from the vertex, you have, it goes up very sharply. Outside that, within that, it hangs around the x-axis a bit longer than a parabola does. All right, good deal. Any questions? Does it make sense? Got it? All right. Now, what we hopefully have been noticing, I'm sure you have, is how important certain features of these equations are, or functions are. And this is going to lead to what they call the leading coefficient test. I like to call it the leading term test, because I think the whole term is important and can give you clues. The coefficient does give you clues, but not everything. Okay? Now, in the first example, that and that, okay? Note that both graphs eventually rise or fall without bound as x gets large negatively or positively, okay? All polynomial functions do that. Whether the graph of a polynomial function eventually rises or falls can be determined by the function's degree, whether it's even or odd. See, that's in the leading term, not just the leading coefficient. That's in the leading term. It's degree. And by the leading coefficient, whether that's positive or negative. And we just saw that as a case. And they say indicated by the leading coefficient test. I like to call it the leading term test. Okay. So, here's the deal. Here's a polynomial function. Alpha of x equals a sub n, x to the n plus a sub n minus 1, x to the 1, blah, 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 plus a to the 2, x squared plus a to the 1, x to the first plus a to 0, x to the 0, which is 1. Okay. Here's the deal. When x gets very large positively or negatively, okay, I'm doing right, well, I'm facing backwards. Okay, these fall out of, this takes over, because that is raising x to the largest power. Now, 10 is not a very large number, but give me an exponent, any old exponent. 2. Okay, when you square 10, what do you have? 100. Okay, you would have, if this was just a 2 here, that's the smallest n you can have almost, okay? If that was a 2, the next one's going to be x to the first, which is going to be 10. 100 is going to completely swamp out 10, right? So, it all depends on that leading term, or a lot depends on the leading term. Okay, let me back that off. The end behavior depends on the leading term. What happens for very small x's and very, very large x's all depends on this term. Okay? Now, what about the term? Well, what is that n? Is it even or odd? Now, we just saw when n was even, which way is the function going? This was, the n was 4. It's going up and up. Okay? Both directions. Okay? Both sides. Okay? Because you square a negative number, you raise a negative number to the 4th power, is positive. Positive number to the 4th power is positive, okay? So it's going in the same direction. If you had put a minus sign in front of this, then it must be going down, okay? So when the exponent is even, then your end behavior is going in the same direction, whether it's up or down. And that depends on the sign of the leading coefficient, okay? So, that was when it's even. They started out odd, so let's go to where it's odd. This one was odd, right? Now, what do you notice here about the end behavior? One's going up, and one's going down. If you hadn't had the minus sign here, it would have been flipped, okay? Because if you raise a negative number to the 5th power, it's still negative, okay? But if you negate it, then it makes it go positive. Same thing with a positive number. Raise it to the 5th power. Whoa, it's positive, but you negate it, and then it turns negative on it. So these always, if this leading coefficient is, leading exponent, the degree of the polynomial, the exponent of the leading term, is odd, then you know these are going in opposite directions. If it's even, they're going in the same direction. Okay? That's what the degree of the polynomial tells you. So if n is odd, the degree is odd, then whatever else is happening in here, we really don't care about that much. In the long run, this is going south, that's going north, if that leading coefficient is positive. Okay? Because very large positive numbers here, when you raise it to an odd power, it's going to be very, very odd as long as that leading coefficient is positive. Very small numbers here, especially if you get here in the negative territory, and leading coefficient, the n is odd, that's going to take you downhill fast. And if that leading coefficient is positive, it continues downhill fast. However, if you flip that and make the leading coefficient negative, then it flips everything. This very, very large negative number becomes a very large positive number. The very large positive number becomes a very large negative number. Because always when it's odd, they're going opposite directions, depending on which directions they go depends on the sign of the leading coefficient. Now, I feel like I'm giving semaphore up here, right? Y'all don't know what semaphore is. Never mind. All right. So when n is even, though, raising it to an even power, then you're either on the up and up or down and down, okay? It's got to happen that way because you raise a very negative number to an even power, it's positive. And as long as that coefficient is positive, it stays positive. Raise a very positive number to a very high degree, and it is really positive as long as that leading coefficient is positive. But you make that leading coefficient negative, this very positive number that you had here flips over and becomes negative, and that very positive number flips over and becomes negative. So then it's going to be down and down. Now, what happens in between here? That's all those other terms, okay? Those are going to contribute to that. Okay, we have someone hiding outside the door here. Okay, here he is. Somewhere I had a pen here. There it is. Darius is here. Okay. Well, if I was on the right page, I could mark you. All right. Does anyone else come in since the call roll? Okay. Okay. Good deal. All right. Any questions on the leading term test? I don't like to call it leading coefficient. Yeah, leading coefficient is important. The sign of it is important, but the power is just as important. Okay. So that's n is even or odd. So leading term test. Any questions? All right. Now, here, all we're going to do is describe here's what they call it, the right hand and the left hand behavior as you get very, very large to the negative and very, very large to the positive. Okay? What do you think this function's doing? What's it going to the right? F of x. Hey, where's the function heading? Second? Down, way down, because you get a big number in here. You don't have to choose a big number. 10 will work. 10 to the third power is 1,000. So here you have negative 1,000. I don't think this is going to make any difference at all. Minus 40, nah, that's not going. Plus 40, that's not going to hurt. What if this was going to the left? You're going very negative on x. Is what? Up. You're absolutely right. Way up, yeah. Because a negative 10 raised to the third power would be negative 1,000, but then that negative makes it a positive 1,000. So yeah, it's going like that. Okay, how about this one? What's this? Right hand behavior. Up or down? Up. How about its left hand behavior? Up or down? Up. Very good. How about this one? Right hand behavior. See? Yes? Okay. Huh? Up. And left hand behavior. Say again?
Left.
I couldn't hear.
Left.
Okay, left hand behavior. Where is it going? Up or down? Where's the function heading? Down. Absolutely. Absolutely. All right. Now, how do we express this? Okay? I meant to point that out on the previous slides. Okay? Here's how we talk about it. We say as, I like to start this way. As x approaches infinity, in other words, it's very large negative, what is the function doing? It's going very large negative. That's the y value. As x goes very large positive, so does the function. Very large positive. This one, however, as x goes very large negative, the function is going very large positive. And here, as the function is going x is going very large positive, the function is going very large negative. You see how they write that? Okay? These two, As x is going very large negative, where's the function going? Very large positive, positive infinity. As x is going very large positive, where's the function heading? Very positive infinity there too. As x is going to negative infinity here, where's the function going? Negative infinity. Where's the function going to positive infinity here? Where's the function going? Negative infinity. Okay, so that's how they express it. They usually put the function first and then the thing. I say you start with the x. Give me an x and then I'll tell you the y. So I like to start the other way just because I'm contrary. Okay, so here's what we'll do here. As x is going blank, f of x is going blank. And as x is going blank, f of x is going blank. Okay? That'll be the first one. The second one will be like as unto it, and the third one like unto it. So let's just do the first one now. You tell me what to fill in the blanks. Can I give you a hint? Now this is for polynomial functions. Okay? For polynomial function, what's in the blank is always an infinity. Because when x is very large, so does the function. When x is very small, so does the function. It gets to large numbers. All you have to do is give me the signs. And here is another hint. One of these x's is going negative. I don't care which one. The other's going positive. So guess what? You have two answers correct every time. If you put one of these x's negative and one positive, and everything's going to an infinity. And then what you're asked to do is what are the signs of these two? For A. All right, good deal. And remind me of your name? I thought so. Okay. There you are. All right. Anyone else come in when I wasn't looking? Okay. All right. See what it does? Now, what you have to do is give me the signs to put here, the SIGN sign for number A. As x is going to very negative numbers, what is your function doing? Positive, so we leave it just like that. As x is going to very positive numbers, this is for A again, what is your function doing? Negative. That's all you do. Ding. Done. You've got it. You know all four of these for polynomial functions. For polynomial functions, all four of these are going to be infinities. Know that ahead. They're going to be infinities. One x is going to be positive, one negative. I don't care which you put where. The whole experience is to determine which sign the f's are. Do they say positive? Is one negative? Is both negative? Whatever. Which one is which? Okay, so what I'm going to do is erase my signs. Well, I'm going to erase one sign. That one, okay? And let's do number B, okay? I'm being really, really lazy here, as you can tell. Okay? For number B here, we know that all four of those are infinities, and one x is negative and one's positive. We know that off the top. My question to you is, what signs do we have the f of x here for number B? As x is very large negative, what sign is your f of x? Question. Say again? Plus. Okay, that's done. How about when x is very large negative? How about very large positive? What's your f doing? Yes, yeah, raised to the fourth power, everything plus, unless that leading coefficient is minus, it's not, so it's going up. So those are correct just like they are. You see? Okay. And you see, all four of them are going to be infinities for polynomial functions, okay? And one x is going to be positive, one negative. You have to determine the signs of your f. That's all you have to do. All right. This time, let me... Oh, I don't have anything to erase, do I? Okay. For number 5. Okay? Number C, x to the 5th. Okay? We know all four are going to be infinities. For polynomial functions, they will be. and one x is going to be plus and one's negative. It doesn't matter which order. When x is going negative, where is c going? Second. When x is going negative, that's an odd exponent. So it's going negative. You raise a negative number to an odd exponent, it stays negative. So this one goes negative. Yak. Why is it doing? Oh, I know why it's doing it. For some reason, it loses the pen sometimes. Okay, it goes negative. And when x is going very large positive, what's that going? Positive, yeah. I mean, if nothing else, just plug in a 10, okay? And a negative 10. Negative 10 to the fifth is negative 100,000, okay? But it's negative, okay? So that's definitely going negative. And plug in x 10, not negative 10, but 10 to the fifth is positive 100,000. So that goes positive, okay? Whatever it is, really, if it's odd, they're going opposite directions, those signs are going to be opposite. If it's even, they're going the same direction, you just don't know what sign, okay? And on the odd, you don't know which is positive and which is negative, but they're one each. So you know that's going to be the case. The sign out here tells you which way to go. Okay, does that make sense? So that was a C, okay? Let's see how they do it. Well, they drew the function, okay? That's fine. And I should have brought that up too. What kind of function is this? Odd, because that side and that side. 3 and 1 are both odd, so it's an odd function. It's going to be symmetric about the origin, okay? Just as Q comes in, okay? All right. And that means for, now again, your end behavior doesn't tell you anything about what happens in here. All it tells you is what happens in the long run, okay? When x is very large negative, then this function is going up because x cubed, any negative number cubed is negative, but then you negate it and it's positive. Any positive number cubed is positive, but when you negate it, it goes negative. That, to me, is the easiest way to look at it. Just look at that middle leading term and see what you get. Okay, let's see if they write out their statement then. No, they don't. Okay, the B one, what can you tell me about it? It's even. That's even, that's even. And what's the exponent here? 0, and that's even. Okay, so this is going to be an even function, meaning it's reflective across the y-axis. That really doesn't matter too much. What we're interested in here is, when x is very large negative, you raise a negative number to the 4th power and it goes positive. So this is going positive. And when you raise a positive number to the 4th power, it stays positive. No sign in front, so they're both positive. Plus and plus. Okay, this one, they happen to give you 3 odd functions, or 3 even or odd functions. Most functions are going to be neither, okay? They just happen to give you 3 that were either even or odd. 2 odds and 1 even. Odd, odd. Doesn't really matter, but we do know when you raise a negative number to the 5th power, going downhill. Raise a positive number to the 5th power, going uphill, and your sign of that leading term is positive, so it doesn't change direction. Does that make sense? Beating a dead horse, right? Okay. Now, in this example, note that the leading term test tells you whether the graph eventually rises or falls to the right or left. Other characteristics of the graph, such as your intercepts, your minimum and maximum points, they got to be determined by other tests. Leading term test only tells you what happens in the long run, not what happens in the middle, okay? Have to do that with other analyses. And that's what we're going to be doing next. We're going to see if we can find the zeros of a polynomial function. Remind me, what do we mean by the zero of a polynomial function? What's another name for that? The what? Why? Yeah, why not? No. It's close. Okay? It's where y is equal to 0. Okay? And where y is equal to 0, what else does that tell you? Where are we if y is equal to 0? On the what? What? X-axis, exactly. So you can also call these real zeros of a polynomial or any function the x-intercepts. The zeros are going to be your x-intercepts. Keep that in mind. Okay? So that's where we're going to look for the real zeros of polynomial functions. Now, here's a couple of statements that are true. Okay? If you have a polynomial function of degree n, that's the degree of the polynomial, that leading term's degree, okay? That's the nth degree polynomial, okay? If you know that, then you know the function has at most n real zeros. Doesn't have to have n, but it can't have any more than n, okay? It cannot have any more than n. It may have n or something fewer than n, but it will have at most n real zeros. Now, because it has that many zeros, that means it has to change direction n minus 1 times. So if this was, give me an n, any n. Give me an n. 2. Okay, it's going to change direction 1 time. Well, what kind of function is maximum exponent 2? Second? Okay, it's an even function, but more specifically, we just did it in the last section. Quadratic function. And what does the graph of a quadratic function always look like? Parabola, which has one turning point, the vertex, either that way or this way. So if it's degree 2, it could have 2 real zeros. It may not. It may only have 1 or it may have none. Okay? But it always will have, well, it has a quadratic function always has one turning point. Now the others don't have to. They have at most n minus 1 turning points. Turning points are also called relative minima or relative maxima. Okay? Now, that's not a car's name, or it is a car's name, but they named it after this night, didn't name this after the car. These are plural. I think it's Greek or Latin one. When they make something plural, they put an A on it, not an S. Okay? These are points at which the graph changes from increasing to decreasing, or vice versa. So finding the zeros of polynomial functions is one of the most important problems in algebra. So we're going to be focusing most of the rest of our attention on that for the next several sections here. Okay? There's a strong interplay between the graphical and algebraic approaches to this problem. We'll try to sort of mix them up with both. You know the book's going to do the graphical. Okay. Real zero is a polynomial function. When a polynomial function, when f is a polynomial function, a is any real number, the following statements are all equivalent. I wish they hadn't used a, but they did. Okay, so it's fine. If you say x equal a is a zero of that function, these other three things are automatically true. The first one, x equal a is the solution when you set that function equal to 0. Well, that's what it means to be a zero of the function, where the y is equal to 0. F of x equals 0. Well, that's how we go about finding it. You set the function equal to 0, see if you can solve that function. Okay? So these two statements are exactly equivalent. Okay, here's another one. X minus a is a factor of the polynomial. If x equal a makes this 0, remember what we did? If we factored that polynomial and had x minus 7 as one of the factors, then you set x equals 0, and that makes x equals 7, a 0. So if x equal a is a 0, x minus a is a factor. Automatically. Automatically. So this is going to help us factor those really big, ugly, hairy, mean-looking polynomials. And here's the other one, the one we just said. A comma 0 is an x-intercept. All these four say the same thing. If that's true, the other three are true. If that's true, the other three are true. If that's true, the other. Any one of them true, all three of them are true. Make sense? All four ways of saying the same thing, just from different perspectives. Okay? So here's our first problem. Find all the real zeros of that polynomial function. We don't know how to do quartic functions, do we? Sure we do. What would you do first? Say again? You may have said it right. I just can't hear well. Set it equal to 0. Excellent. Oh, I gave it away then, didn't I? Okay, and then what do we do? What's the F word? Oh, factor it. Yeah, that's right. Okay, and what would you do to factor that? Can you factor a 4th degree polynomial? Okay, let's factor out a negative 2x squared. You're absolutely right. What do we have left? X squared. Second? Minus 1 equals 0. Okay, are we through factoring? Yeah? No? What else can we do? Factor that binomial there. Minus 2x squared. We can't do much else with that. We could do a little bit. What does that become? X plus 1 times x minus 1. That's equal to 0. Okay, now we have an equation with 3 factors, and the total equation is equal to 0. What does that tell you about one or more of those factors? To get a product of 0, only way that can happen is what? If one of those was 0. So let's set them each equal to 0 separately. Either minus 2x squared is equal to 0. If that's the case, what would x have to be? 0. X equals 0. And by the way here, this is a multiple. You could have x equals 0, the first x equals 0, or the second x equals 0, because that's x times x. So that's what we call a double root. Okay? Sort of sounds like a chewing gum. No, that's double mint. Never mind. Okay. So, there's one possible 0. Another one. X plus 1 equals 0. What would that give you? X equals negative 1. We subtract 1 from both sides, right? Or, these are all ors here. X minus 1 equals 0. And what would that give us? X equals 1. So there we have 3 possible zeros. X equals 0, x equals minus 1, and x equals positive 1. Now, it says here, then determine the maximum possible number of turning points for that. What would you think that would be? Say again?
1.
Why 1? The maximum number of turning points is always n minus 1. N minus 1 would be 3. 4 minus 1 is 3. The maximum possible number of turning points would be 3. Maybe less than 3, but the maximum would be 3. Okay? Now, what's that? No, we could have had 4 zeros. And see, one was x equals 0, and the other was x equals 0. So we did have 4. It's just the 2 of them were the same thing. Okay? But these are 1 each. So the maximum number of zeros is the degree, 4. Maximum number of turn points is 1 less than that, 3. Okay? Now, they didn't say graph it, but I bet you they're going to graph it. So let me graph it. Can y'all hang on? What I think I'll do is erase most of my writing here. And remember 3 turning points. We'll see if we wind up with them. I'll just keep the 3 zeros in here because I need those in my graph. Okay. Before I draw my graph, though, I want you to tell me what is the end behavior of this graph. Where is it heading? As x gets very large negative, where's this function going? Second? Down because of that minus sign there. Yes, raise a negative number to the even power. It's always positive, but that then negates it. Okay? Remember, it's please excuse my dear Aunt Sally, whatever she did. You do this first, then you do that last, and that changes the sign. So when x is very large positive, which way is it going? Up. Why? That's even, so that would normally go up, but this is, that sends it down again. So this is even, so it's going in the same direction, down and down. Okay? So therefore, I'm going to do my axes, since I know in the long run it's going downhill. I'm going to set my axis as far up there as I can without getting in trouble. Okay, so let's check off 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6. Up 1, 2, 3, 4, 5. We probably won't need those. We'll probably need way more than that. Okay? Now, we know 3 points already, don't we? What are they? 0, 0 is 1. Negative 1, 0 is 1. And positive. Remember, if they're zeros for the polynomial functions, they're x-intercepts, which is 0, 0, 1, 0, negative 1, 0. Okay? So we have the 3 zeros there. Now here's something else that you don't know yet, but I'm going to tell you ahead of time. Remember, this was a double root? So we call that a multiplicity of 2. Okay? Because it had a factor of 2. That means when it reaches here, it's not going to cross the axis. It's just going to come down and kiss the axis and then head back the same direction. These two are multiplicities of 1. They're going to cross the axis there. The even multiplicity, it touches but doesn't cross. The odd multiplicities cross, always. Now, we already told me, what's the end behavior? Down and down. Okay? We know that. It's got to be going downhill both directions. Everybody see that? Okay. Now, if it's got to be going down and it has to cross here, that means it's going up here. Has to be. And if it's going down here, that means it's going down here. Okay? Has to. Okay. Now, since it's kissing here, touching here, that means it goes up somewhere here and then comes down and doesn't cross and goes back up and down. And guess what? That's 1, 2, 3 turning points. Yep. That's what we said, 3 turning points. Even though you only had 3 zeros, you still have 3 turning points. Okay? Don't have to have 3 turning points. You could have had 4 zeros, but that's what you got. Now, that's a really rough drawing. Let's see what they do. I think I'm going to have to erase. Anyone need this a little longer before I erase it? It's pretty ugly. Okay? To find the real zeros of the function, set f of x equals 0. The first thing y'all did, excellent. Then what we do, remove the common monomial factor, which is minus 2x squared. Always a good idea to haul that sign out there if the leading term, that leading sign was negative. Okay? And then we factor it more completely, and you get x plus 1 times x minus 1, just like y'all got. And then we set them. So the real zeros are x equals 0 from the first one, x equal 1 from the second one, and x equal minus 1 from the third one. All right? Good deal. Because the function is a 4th degree polynomial, the graph of f can have at most 4 minus 1, which is 3 turning points. And we see this one actually does. There's the graph. Similar to what I did, but not quite. Okay? It's going down here and down there. That's our end behavior. You know it has to be going there. It's crossing here. The book hasn't told us that because that's even multiplicity. It's touching and going back up here because it's an even multiplicity. And then it's crossing here, odd multiplicity. So turning point, turning point, turning point. Where it changes its direction and heads in the opposite direction. Make sense? Now here's the other thing. Because this is a polynomial function, make sure that you make those turning points nice and smooth. Not pointed, not sharp, not angled. They're smooth, continuous functions. Make sense? All right, that was example 3. All right. In example 3, though, that because the exponent is greater than 1, the factor negative 2x squared yields a repeated 0. That's what we're talking about. X equals 0 and the other x equals 0. Both of those x's are 0, so that's called a repeated 0. When you have that, any factor, this would just happen to be x, but this could be an x minus a, raised to the kth power, as long as k is greater than 1, that yields a repeated 0 of x equal a. Remember, that should be 0. If that's a factor, x equal a is a 0. Repeated 0 of multiplicity k. Whatever that exponent is, that's the multiplicity. So, When that k, again, even or odd, comes into play here. When that k is odd, that means the graph crosses the x-axis at x equal a. But if that k is even, like we had here, that means it touches the x-axis but does not cross it. Now, when this k is odd, our other two were at 1s, and they just crossed straight away. When that k was a 3, here's what it's going to do. It's going to go up and then hang around, but then still cross. If it's 5, it'll hang around a little longer and then cross, okay? So you still have the same behavior you have for the cubic function of the fifth order or something. You still have that same type behavior, but when it's once, it just crosses just like it was a straight line. Okay, so I always talk about multiplicity of 1 even. They only talk about multiplicity of more than 1, but you can say multiplicity of 1. It's just like the coefficient of 1. You don't write it, but it is there. Okay, so the graph of polynomial function, use the fact that the polynomial function can change signs only at its zeros. Doesn't have to change signs, like at x equals 0, it stayed positive on either side. So between two consecutive zeros, the polynomial is going to be either all positive or all negative. It can't change otherwise, okay? If it changed, that means you have another 0 in there, and then they wouldn't have been consecutive zeros. All right, that means when you put the real zeros of a polynomial function in order on the number line, they divide the x-axis, the real number line, into intervals in which the function has no sign change. So that one that we had, we knew the end behavior was negative. That's why I said that last one has to be going downhill. Because it can't cross again, it has to be going downhill. Or actually here, it's going uphill from here. Okay? Then that next one, it didn't change sign, but still it was positive between these two and positive between those two. And then once it passed that one, had to stay negative forever. Because the has no sign changes other than in between the zeros. These resulting intervals are called test intervals, in which you can choose a representative x value and determine whether the value of the polynomial function is positive, graph is above the x-axis, or negative, it's below the x-axis. Remember, y'all did that on a quiz or a test. You did that, same thing. All right. Before we get to the intermediate value theorem, we have two more examples. All right, so let's do them here, or at least the first one here. Example 4. Sketch the graph of this function. F of x is equal to 3x to the fourth minus 4x cubed. Okay? Now I'm going to go on and set up my axis. Okay? Now, it says sketch the graph. They don't mention this, but here's what you should do first. What's the first thing we learned about graph? The end behavior. Where is this one going in the long run? For very negative? Yes, it's going up and up, because that is an even exponent with a positive coefficient. Okay? So we know it's going up here and up here. In the long run, it's log Lewis. No, it's going up. Okay. So we got that down. What's the next thing we do? Y'all did it so well last time. Set it equal to 0. Okay? And then what? Factor it. Okay? And what would be what do you look for first in factors? Second? X to the cube, right? And what do you have left? What? 3x, I'm sorry, I can't hear. Minus what? 4. And that's equal to 0. Okay? What does that produce as zeros now? Either x cubed is equal to 0, or 3x, I can't write, minus 4 is equal to 0. One or the other, or both even. What does that first one tell you? x equals 0. But what do you know about that? A multiplicity of 3. So it's a repeated 0, 3. Okay. And the other one gives us, what would we do? Solve that equation. It's sort of, say again? Add 4 to both sides. Let me get that ugly mark out of there. Okay, add 4 to both sides, and you get 3x is equal to 4, and then divide by 3, and you get x equal 4/3. Okay. Now, let me tick off some points here. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5. Okay, whatever. And we'll go up 1, 2, 3, 4, 5, 6, 7, 8. Down 1, 2, maybe 3. Okay. What's the easy ones to plot first? X equals 0. Okay. And then x equals 4/3, right? Well, there's 1. 4/3 would be right about there. 1 1/3. There's our other 0. We know the end behavior is coming down from the left. Okay, it has to be. And it reaches this 0. And what does it do at that 0? Does it hang there and go back up, or does it cross? Crosses. But it does hang around there a little ways. So what I'm going to do, now this isn't how the book does it, but you know it has to be coming down because it's coming from there. So it's going to be coming down pretty rapidly, but then hangs around this, but ultimately does cross. Okay? But then it's got to be going back up, but this has multiplicity of 1, so that means it's going to cross and go up. So there it is, going on the up and up, and that's how it looks around 0, and it just crosses there as fast as it can, okay, because it's multiplicity of 1. Sort of like a straight line. Now that's a really rough idea what this looks like. Are we, don't tell me, are we already running out of time?
9:44.
Oh, how sad. Okay. Just when we're beginning to have fun. But we always have fun, don't we? Okay. If you look in the book, you'll see this. What the book suggests that you do, by the way, is pick a test point out here, like -1, plug that in, your function, see what it gives you. I bet you it's going to be something along there. -1 would be 3 plus 4, that would be 7. So that would be somewhere up here. Pick another one in here, like x equals 1, see what that gives you. Pick one out here, x equals 2, and see what it gives you. You don't have to do that. You got the general idea. All right, thanks. All right. I didn't give you homework exercises. You can listen to them. Any of the odds, I had to do all of 9 through 14. The odds are in the back and at calcchat.com. Do any of the odds 15 through either 15 or 17. They're both on CalcChat. 17's at CalcView. Do any of the odds 19 to 23. I'm sorry, 27. They're all at CalcChat. 21's at CalcView. Do both 29 and 31. They're both at CalcChat. And then start doing 33 to 47. They're all at CalcChat. 43's at CalcView. If you want to hang up, then we can, and we'll pick up the rest of those later. Oh, good deal.
Can you not put these on here?
What's that?
Can you not put these on here? Because one of them is excused.
Those what?
Can you not put these on here?
Why not?
Because one of them is excused.
That's all right. They know that. Okay. All right. And which is your sport?
Volleyball.
Volleyball. Fantastic. I love volleyball. I love most sports. All right. Let's see how you're doing. Goodness. Miserably poorly, right? There you are. Just going to guess about a B. Very good. Thanks.
Thank you.
All right.